hypothesis behind my presentation is space travel or deep space communication. Space travel and deep space communication mean interstellar. So when you travel to space, you have the problem with the propulsion. You have the problem with the life of any human being in the spaceship, but you also have the problem with the communication. So you must keep the link to the spaceship to control the direction of the spaceship. And also you have to keep the link for communication, because if you want to download data from the spaceship or communicate, you need a very powerful communication. You need to keep the link. So either you build big antennas, or you exploit very wonderful properties of nature, that is the gravitational lensing. Gravitational lensing here. Let's just look at this picture. We have the sun that is approximated as a homogeneous sphere, non-rotating. It's still. Rays are coming from infinity on your left and approach the sun. Of course, they cannot go through pass through the sun. So the very first rays, they are straight rays, and they go along the optical axis, which is the line going through the sun to the focal spacecraft. Then the rays that are in between the focal line and the radius of the sun cannot go through, simply because they are blocked by the sun. As soon as the rays are slightly more distant, they pass through. But since they feel the gravitational field of the sun, they bend. And then they bend, and at a certain point they cross the focal line, and because some of them are blocked by the sun, the minimal distance is called the focal. So the more you get far from the focal line, the longer will be the focus on the focal line. Therefore, you do not have a single focal point, you have a focal line. What is good about this? It is because it behaves like an antenna, giving a gain for your signal that is coming from infinity. So, well, first of all, just a historical remark. This situation I'm describing was first analyzed by the German scientist Schwarzschild, who was able in 1916 to give the first exact solution to the Einstein equations for general relativity. And he did that while he was a volunteer in the World War I. I'm not sure where in Europe, but almost very soon after he uncovered these exact solutions, he felt sick. He returned home and died again in 1916. So what if he hadn't found this solution before he got sick? I'm pretty sure someone else would have uncovered that, but well, that was a luck that we could have this solution. So as I said, you want to communicate, you need to amplify your signal, and you do that by an antenna whose gain, as in the equation on top left of my slide, goes like the square of the frequency. On the right-hand side, I have the gain due to the gravitational lensing of the sun. So I'm in this picture, I'm analyzing the situation from a geometrical point of view, which means that the lights behave just like particles, no wave effects at all. It's a simple approximation of the behavior of the light. So on the right equation is the gain of the antenna that goes like the frequency itself, not the square. But if we put the values of the constants in the gain antenna formula, so for the gravitational constant G, that goes like 10 to the minus 11, the mass of the sun that goes like 10 to the 30, and of course the speed of light c that goes like 10 to the power of 8, and you do some arithmetics, you have the values that you can see in the table for the sun gain and the 12-meter antenna gain, so that we can compare them. Well, of course, it's literature values that I used, and I think that the 12-meter antenna was used, well, it might be because, sorry, it might be because the Voyager. Oh, I'm sorry. I missed something. Here, the minimum focal distance for the sun is 550 astronomical units. The Voyagers that are still roaming far from the sun reached almost 150 astronomical units of distance from the sun. Well, it's about 1/3 of the minimum focal distance, but it proves that space flights are feasible, space missions are doable, and because they are still working. Their engines are still pushing them far from the sun. And well, their antenna, the antenna of the Voyager 2, I'm not quite sure about the Voyager 1, has almost a diameter of 4 meters, which turns into a 12-meter square area of the antenna, and that's the reason for that 12 meters antenna gain. Well, if we compare, the sun is pretty much higher than the 12-meter antenna. And of course you can combine them, since that quantities I'm showing you are in dBs, which means 10 times the log of the power. So let's say, for example, the 57 dBs means around 1 million gain for the power due to the gain of the gravitational lens of the sun. So you can exploit both of them, and you sum up them, and you end up with a gain of around, let's say, for the hydrogen, 100 dB. For the 5 gigahertz frequency communication, it's around 115. Well, hydrogen, why hydrogen? Hydrogen, that's because hydrogen is the most abundant element in the universe. So we might guess, but it's an hypothesis, that if an extraterrestrial civil intelligence wants to communicate with us, it might do that using the hydrogen frequency. Well, 5 gigahertz is a common frequency for terrestrial communication, and then there's the water. The geometrical treatment of the gravitational lens of the sun is an approximation. And, well, you might argue that the bigger the frequency is, since the gain is goes like the frequency, the bigger the frequency is, the bigger the gain is. And that cannot work perfectly, that not correspond to what happens. because if the frequency went to infinity, we would have an infinity gain, and that's not physical. So we want to give another solution that takes into account also the wave behavior of the light. And we have wave effects. Again, if we analyze again a Schwarzschild solution of a non-rotating static mass, using general relativity and wave treatment of light, we get that equation that is the behavior of the magnetic field into space. Now, apart from the difficulty of this equation, well, today is a cloudy day, but just imagine when you are at the sea and the water is up to your knees, all of a sudden you look down and your feet are not longer below your hip. So I'm exaggerating, but what happens is that it looks like your feet are slightly moved on a side, and that's because when passing at the border from water to air, the image of your feet is tilted as if it came out along another direction. That's called the refraction phenomenon, and it happens every time you are at the border between two media with different refractive indexes. Imagine you have a sequence of borders, of layers, with different refractive indexes. What happens is, at the first border, we have a tilt. At the second border, we have another tilt. At the third border, we have one more tilt, and so on. And it looks like your light is bending throughout all these parallel layers. Well, that's what gives birth to, for example, the Fata Morgana mirage, or to waveguides, just like the optical fiber, or whatever it is. It's something that describes how the direction of the light is a curve. But while using the parallel borders between different media, we are describing a situation that is only optical. I can guarantee that it can be proved that this equation is obtained starting from a description of a gravitational field. Since the two equations are fully comparable, it means that a gravitational field can bend the light. And that's what happens. The light, once it passes the sun, it's curved through the focal line. Well, it's only mathematics, but this wave effect treatment is necessary to avoid the divergency. So when the frequency grows higher and higher, the gain will not grow as much. Nevertheless, another theory that is the wave description of the light tells you that we have a gain due to the gravitational field. That's simply because all the power that was dispersed in a beam is concentrated in one only point. Okay, in one only line, but basically in one only point. And all the power is collected in one point, and the gain blows up. By the way, because we are considering the optical wavelengths, the corona of the sun effect is negligible. If we wanted to, the same idea can apply to radio frequencies, that are frequencies that are lower than optical frequencies. So we could maybe have to cope with the corona effect that tends to open the beam instead of focusing. But since we are looking at the optical waves, right now we can be assured that no corona effect is in place. So if we use this theory, this better description of light behavior, we have this picture of the gain of a optical beam through the gravitational field of the sun. We have a wavelength of 1 micrometer, a gain that is 110 dBs. Unfortunately, well, a so big gain does not correspond to an easy situation, simply because if you look at the main lobe of the gain, it falls very rapidly to zero in very in a very short space. Goes like the meter, the unit of measurement of the x-axis is the meter, which means that it rapidly goes to zero, and it's a periodical behavior, but every period it falls to zero, and which means that you have a very small antenna that falls within the zero energy of the antenna gain. You cannot measure anything. So you should be able to point your antenna on the main lobe, which is engineerily very hard to achieve. If we transmit at smaller frequencies, and that means higher wavelengths, the main lobe is larger, even though the gain peak is slightly smaller, so that the energy within the lobes keep constant. Finally, even though I do not have so I said that the optical waves can be useful, the antenna gain of the sun can be useful for optical waves. The same behavior can be described for radio frequencies. There's some literature also about neutrinos that can be the carrier of the information for a certain civilization that would like to communicate with us in case from far distances, simply because neutrinos have a very low extinction coefficient, which means that they are not absorbed so easily. They are not absorbed so easily. In fact, not far from a location that big historians may know very well, that is in Umbria, the Gola del Bottaccione, where Alvarez was able to demonstrate the reason for the last mass extinction. There's the Gran Sasso facility laboratories for the measurement of neutrinos. And in fact, we have a very huge laboratory, unfortunately I've never been there, that are below the Gran Sasso Mountains. And the idea is to exploit the mass of the mountain to slow down the speed of neutrinos so that they can be measured. But the reason, to get back to the main idea is we could also receive communications from extraterrestrial intelligences that would like to transmit using neutrinos carriers and exploit the gain of the sun gravitational field, giving us a very huge gain. The description of the neutrinos gain is very similar to the gain of the optical waves. And that's it. That's a physical phenomenon available. Thank you. I was the last one before the coffee break.
Will you just give me 3 minutes to tell a story? Story, not mathematics. No. So
you should bring here a chair.
Yeah. So let me tell you a story. All true story. Okay. I discovered this idea of using stars as a gravitational lens by reading a report that was describing what Einstein had done as early as 1936. So you may say, okay, that's not your idea, it's Einstein. Einstein was a wonderful mathematician, and he knew, of course, all these equations. But he did not have the idea of space flight. So big historians should be careful about this kind of things. It's hard to give right merit to the right person. I know. But this is one of the tasks of big historians. So Einstein published the papers, and the story itself is laughable, because he actually discovered the equation in 1912 when he was traveling on a train from Prague to Berlin, on a train, right? He discovered it. But never published that, because he considered that to have the perfect alignment between one star source, the second star doing the gravitational lensing, and the Earth was such an improbable event that it would never have happened, period. And of course it was wrong. Okay, but that was in 1912. So anyway, he then came to America, as you know, or went to America. We are in Europe, here. So anyway, in 1936, he received the visit of a SETI engineer, so baseball journal, by the name of Rudolf Mandel. And this guy had rediscovered practically on its own the effect of the gravitational lens and of any star, not just the sun, of any star, according to general relativity. So he had this conversation with Einstein, with due respect to Einstein, sir, why didn't you publish it? And Einstein, took it easy, and finally decided to publish that on Science. And he Einstein wrote a letter to the manager of Science saying, look, please publish this paper, so this guy is not going to bother me anymore. So all this is true story. Look on the web for Mandel. Okay, and then poor Einstein died in 1955. And the Sputnik came later, so Einstein did not have the least idea about space flight. This should be kept in mind. Okay, many years later, the story was rediscovered by an American scientist at Stanford, Sidney Leeds, whom I had the privilege to meet during one of my visits to Houston. And Sidney Leeds considered the gravitational lens not of stars, so not of spherical bodies, but of galaxies. So you have a source on the other side, a quasar, extremely powerful. Then you have a galaxy perpendicular to the line between the quasar and the galaxy. And then on the other side you have the Earth. So the lensing thing is the galaxy. And this was searched until 1978, when a British astronomer was able to prove it by observation. Wonderful. In the meantime, a professor at Stanford University by the name of von Eschenbach published a paper where he described for the first time what Nicolò said, that is the minimal focal distance that the spacecraft must reach in order to exploit the sun's gravitational lens is 550 astronomical units for the sun mass. Of course, if you change the star, it's a different number. Now, what does that in practical terms mean? It means that in light terms, it's 3.17 light days, so nearly half a light week, which is far beyond what has been reached so far. because the Voyager reached 350, so we're talking about much smaller distance. So this was published by Sidney Leeds, and when he discovered all this story, and that happened to be on a plane from Rome to Turin, he had nothing to do, let's read this thing. Wow, this is a great idea. So I took a real interest. And my company, which was Alenia Space in Turin, used to send me a number of times to NASA, particularly at JPL, for completely different things, for space mission to Mars, whatever. But I love that to such an extent. So I'm teaching back to the young people. I love that to such an extent that I decided to approach my American boss, who was Roger Burke, I have no problem at SETI, saying, would you please let me give a talk at JPL about the science of gravitational lens? Now he was surprised, well, what is this guy doing? No, he must be an engineer. I am a physicist, not an engineer, and that makes some difference, but with due respect to engineering, please. So, conclusion, I was allowed to give a talk. And before this talk, they asked me, could we record, or could we tape your talk? I said, of course. And next time we meet, I will give you the DVD of the talk, given on August 18, 1998. Now, this was the first talk ever at JPL, that is at NASA, about using the sun as a gravitational lens. Then, of course, the JPL bosses started to take an interest. In particular, Slava Turishev, the guy who escaped from Siberia, is wonderful, and he's working at JPL now. So what Nicolò told you, that is physical optics, not geometric optics. I did the geometric optics, that is the easy version. But the physical optics, which is much more difficult with the equation of the second, was and is given by Slav. He is junior than I by, I don't know, 10 years or something. And the story is not over yet, but we are close to the end. Now, this very rich guy that was mentioned earlier, that is Yuri Milan, is of Russian origin. And he is, and his team, are planning a space mission to Alpha Centauri, the nearest stars, which was never intended before. But in order to do so, they must keep the radio link at 4.37 light years, which is a huge distance. So, Slava Turishev and Yuri Milan, that could speak Russian among themselves, said, why don't we use this idea written in Claudius' book? So over there you'll find my book, Deep Space Flight and Communications. And so I am pretty sure that in 10 years' time, I will have, if I survive, this fantastic pleasure of seeing the first space mission launched in the direction opposite to Alpha Centauri, because this is necessary in order to exploit the sun's gravitational lens, which means minus 60 degrees below the ecliptic. It's not an easy thing. But they are preparing that. And so I'm really grateful to all the people involved. Slava Turishev, of course, but Yuri Milan and all that. Because they are really carrying out the first interstellar mission to the nearest star. Thank you for your attention.